Alright, so now we will develop our custom metric function. I erased some parts here to get some space to put down things. By the way, the complete code was already shown and discussed in our previous part, but here I'm gonna go a little bit deeper on the concept behind how I developed that custom function. So I start developing a custom function for metric by first inheriting the inbuilt metric class that is present in TensorFlow. It is important to inherit the default class of TensorFlow because it provides all the necessary material that this class should have. These material include the definitions, and I'm gonna get to that, and the input arguments that those definitions require. We'll get to both of them here. Now, when I'm customizing my metric, there are three definitions that I have to override or define for my customization, and they are: one is init, the other one is update, and I think it is update state, and finally result. These are the three definitions that I have to overwrite here. Now, the next part is important, which is which thing should go here for my definition. We saw here that FPR, false positive rate, is basically false positives over negatives. This formula tells me the state variables. Let me use a different color here. State variables. Whenever we are defining a metric, it is important to identify the state variables early in the stage. And how is a state variable defined? A state variable is one which is additive, meaning you only have to perform, when you want to update it, you only have to perform either addition or subtraction. The false positive and negatives are these state variables. So in the init function, I'm gonna put false positives equal to 0 and negative equal to 0. This is nothing but initialization. So we initialized our state variables and made the initial values as 0. The initial values could be something other than 0 as well. That depends on the problem and the state variables. In this case, it is 0. And the next function we are going to define is the update state, and then we are going to define result. I put a quick visual here. This visual will help us understand all of this together. We'll get to here shortly. Before we get to here, let's see what happens in the update state function. So in the update state function, as the name says, we are going to update our state variables that we have here. The update state has, now self is always an argument. If you don't know, self is basically a class argument, which means that you can use self to access anything that is present in your class. So this is a default argument. And then we have the y pred, basically the y predictions, and y true as other default arguments that goes into update state function. And by y pred and y true is actually y hat and y for the entire batch. It's a vector of prediction that was made for the entire batch. And that is why it was important to understand the iteration levels in the previous part, because as we discussed in the previous part, the iteration levels happen at epoch followed by batch level, and this function update state is called at the batch level. This is what you have to make a strong note on. This update function is called at batch level. The init function is initializing everything or resetting everything to 0 or its initial value. This happens at the beginning of an epoch. So when my training starts, training will happen in an epoch, and at the beginning of the epoch, before anything has happened, we get inside this class, and the class resets or initializes my state variables to its initial values, 0 in this case. So this happens at the beginning of the epoch. The next part, which is update state, will be called iteratively every time a batch is processed. So within an epoch, we are iteratively processing different batches. At each of those batch, my update state will be called, and when update state is called, it has the true values of my y and the prediction of y for the entire batch passed as default arguments. Now I have the privilege to do any processing on this predicted y and true y inside this update state. So we will take that privilege and update my false positives to its previous value. So basically I can write it down like this. We update it with its previous values plus the false positives that we have for this particular batch that we can compute from here. So the false positives are incremented here for this batch by adding it to itself with the output of this particular Boolean comparison, which is we are finding the false positive, which means my true should be 0, my y true should be 0, while my prediction should be 1. That's by definition of false positives. So this gives me the updated false positive, and negatives are relatively straightforward. Just have to find the number of true y's which was 0 in this batch. So I just have to find this. So here I updated my false positive and false positives and negatives for this batch. When the iterations are going on for model training, batch by batch, this update state will be called repetitively over and over again for each batch until we reach to the end of the epoch. And when we come here, at the end of the epoch, we come to the result function, the result definition, and here what we do is we get the final output, which is simply a division of what we found here, false positive over negatives. This gives me the output I was looking for. There are a few things to note here. One, there was a question I got from one of the students that why didn't we compute this FPR directly in the update state. We could have computed this ratio here and it updates itself. Why do we have to do this additional computation here? And the answer to that is, and that goes back to the initial statement that I said, that making a custom matrix, the first requirement is to identify a state variable or your state variables which are additive, which you can increment or decrement, because in the update state you only want to put something that is additive in nature. Instead, if I had put FPR here, let's see what would have happened. If I was computing FPR here, which means I would have to update FPR as something like this, false positive over negative for that batch. That means I'm adding a fraction in each iteration. This is essentially a summation of FP over negatives for each batch. However, I'm not interested in this. What I'm interested in is summation of false positives over summation of negatives for each batch. Essentially, the difference of whether you want to find a sum of ratios or ratio of sums. Here we want to find ratio of sums. That is typical for all matrix, and therefore we have to have additive state variables here. We cannot compute FPR directly here. And stitching it back to our understanding of how training works, these computations happen, it starts at the epoch level, ends at the epoch level, and in between this iterates batch by batch. And here I have made a little illustration, graphical illustration, to have some intuitive understanding of this entire process. It helps me. What I'm showing here is the init function is more or less like an entry gate. I enter here with my state variables, then some processing happens in the update state, and ultimately I exit from my result function. This whole mechanism is something of this sort.